Alright guys, in this video we're going to talk about the inverses of the trig functions. And when we talk about inverses, we're talking about two relations that undo each other, which means that if we're talking about functions, we're going to be talking about relations that switch the input and the output, right? So in general, when we're talking about the trig functions, we say the input of trig functions, what trig functions evaluate, are rotations, or maybe even angles. And the output, what we get out from the trig functions, are ratios. So if we're talking about the inverse trig functions, we're going to be talking about functions that take as their input ratios and give as the output the rotations or angles where those ratios occur. So right here, we've got the definitions of our ratios of sine, cosine, and tangent. These are the functions that we're going to be looking at finding inverses for. If we were to refer to these guys as f of x, then right here the inverse would be written as f to the negative 1 of x. And that's how we're going to see the notation for the inverse trig function. So if sine takes a rotation theta and gives as its output the ratio, which we define as the y value on the perimeter of the unit circle where that rotation ends, inverse sine, which we would write as sine to the negative 1, is going to take as its input a ratio, which we define as the y value on the perimeter of the unit circle, and give us as its output the rotation where that y value occurs. Similarly, we can say that inverse cosine, which we would write as cosine to the negative 1, is going to take as its input the ratio, which we would define as the x value on the perimeter of the unit circle, and give us as its output the rotation where that x value occurs. And inverse tan is going to take as its input the ratio, which we would define as the y value divided by the x value on the perimeter of the unit circle, and give us as its output the rotation where that y value and x value occur as an ordered pair. Now we have an alternate notation for inverses, and that's going to be arc. So right here, another way of writing inverse sine is arc sine. And arc sine, of course, is taking the y value on the perimeter of the unit circle as its input and giving us the rotation where that y value happens as its output. Another way of writing inverse cosine is arc cosine. And right here, arc cosine takes as its input the x value on the perimeter of the unit circle, which is the ratio of cosine, and gives as its output the rotation where that x value occurs. Arc tan is another way of writing inverse tan, and it's going to take as its input the y value divided by the x value and give as its output the rotation where that y value and x value occur as an ordered pair. Okay, so looking at this, the idea is pretty simple. We take a ratio defined on the perimeter of the unit circle with the x value and the y value, and the output is the rotation where that ratio occurs. But we've got a problem here. If we think about sine, cosine, and tangent, they're cyclic functions. So there are an infinite number of rotations where a ratio would occur. And so in general right here, what we're going to have is a situation where we have to redefine our trig functions in such a way that will allow us to define the inverses in a way that we can evaluate. Now, this isn't the first time that we've run into a situation like this. If we think about y equals x squared, we have the graph of the parabola that goes through the origin. We'd say that this function fails the horizontal line test. And for its inverse, what this means is that the inverse is not going to be a function. When we switch all the x and y values in the ordered pairs, we get a graph that fails the vertical line test, where we have more than one output for an input. What we do to solve this problem is we redefine the portion of x squared's domain that we're going to invert. And right here, what we're going to say is we're going to take the interval of x squared's domain that gives us all of the outputs, all the y values. And so right here, if we take from 0, 0, and go out to positive infinity on the x-axis, we have the interval from 0 to positive infinity, where we can basically get all of the outputs or inputs of x values, right? And right here, when we invert just this section, we get this half of a sideways parabola, which is a function, and this is how we define y equals the square root of x, which is the inverse to x squared. Now what we're going to do is talk about actually getting these inverses and using them. Right? So right here we're looking at inverse sine or arc sine, and if we look at the graph of sine, clearly the graph of sine, this repeating wave, fails the horizontal line test. So in general what we can say is that this function is not one-to-one, and so its inverse is not going to be a function. But just like the graph of x squared, we can cut the graph of sine so that its inverse would be a function. And what we want to do is cut the graph of sine so that we're incorporating all of the possible outputs that sine could give us. Those outputs range from -1 to +1. And so in general right here, what we're going to do is cut the graph of sine between -pi/2 and pi/2 and invert just this section of the graph. And when we invert just this section of the graph, our inverse will be a function. So right here, we'll go over and we will invert our sine, and right here we get a graph that looks something like this. Now the graph itself isn't going to be that important to us. What it does tell us is the domain and range that we should expect from our inverse sine. So right here, looking at this, we can say that inverse sine is going to evaluate y values as ratios from and including -1 to and including 1, right? And it's going to give us outputs that correspond to those ratios as y values on the unit circle from and including -pi/2 to pi/2. Now that means when we're evaluating inverse sine, we're really just using the right side of the unit circle, right? So in general, we'll say inverse sine only produces outputs of -pi/2 to +pi/2, or on the right side of the unit circle. So in general right here, we would say that inverse sine is basically going to be evaluated only on the right side of the unit circle from -pi/2 to pi/2. Now, one way we can think about this is really what we're looking at is the least amount of rotation that will generate the vertical change or the y value. So let's think about the relationship between sine of theta equals y and the inverse of sine, which is going to take a y value and give us a theta between -pi/2 and pi/2. So right here, if we take, for example, the rotation, let's say pi/3, right? We evaluate sine of pi/3 and we get the square root of 3/2. Now right here, if we were to go ahead and evaluate the square root of 3/2 as a y value in inverse sine, we would say to ourselves, okay, what's the least amount of rotation I can do to give me this y value? And the least amount of rotation we can do is a rotation up in the first quadrant that is pi/3, right? And that's the least amount of rotation that will give me that square root of 3/2 as a vertical change. We see that in the ordered pair in the perimeter of the unit circle. And so right here we would say then that the output that inverse sine would generate would be pi/3. So let's say we evaluate a rotation of 5/6 pi. So 5/6 pi is a rotation that takes us all the way into the second quadrant, and sine would evaluate that rotation and give us the vertical change associated with that rotation, which of course would be 1/2, right, which we see in the ordered pair on the perimeter of the unit circle. So right here, sine takes 5/6 pi and gives us back 1/2. Now, what about inverse sine? Inverse sine would take 1/2 and it would say, what's the least amount of rotation I need to do to give me a vertical change of 1/2? And if we go over to our half a unit circle, we would basically see that the least amount of rotation that we need to do to generate a vertical change of 1/2 would be that rotation in the first quadrant that takes us to the first stop, where we have square root of 3/2 is the x and 1/2 is the y, and that rotation would be pi/6. So basically, it doesn't matter what we rotated to get the y value. Inverse sine is always going to evaluate the y value with the least amount of rotation it would take us to give us that y value. So for example, one last one, if we're looking at, say, a rotation of 7/4 pi, we'd evaluate that on the unit circle, and we would get negative square root of 2 over 2. And right here, if inverse sine evaluated the negative square root of 2 over 2, it would say, what's the least amount of rotation I need to do to create that vertical change? And that least amount of rotation is a rotation into the fourth quadrant, where of course we have the ordered pair square root of 2 over 2 for the x and negative square root of 2 over 2 for the y. That amount of rotation as a rotation down into the fourth quadrant is negative pi over 4. So not 7/4 pi, but negative pi over 4. So that's how we're going to evaluate inverse sine. If we look at the cosine inverse, we're going to be basically doing roughly the same thing. Right here, what we want to think is, just like sine, the graph of cosine fails the horizontal line test miserably. And so what we need to do to evaluate the inverse of cosine as a function is cut the domain so that we have all possible outputs. So right here, what we're going to do to get the inverse of cosine is cut our domain from 0 to pi. And we're going to invert just this portion of cosine so that we can get inverse cosine as a function. Now, when we do that, we get a graph that looks something like this. And again, as a graph, it doesn't really help us, but we can go ahead and visually identify the domain and the range pretty quickly. And what we would say is that we are going to be evaluating x values from -1 to +1, right? And we are going to be looking at assigning rotations from and including 0 to pi, because that is the least amount of positive rotation that we need to generate every single horizontal change from -1 to +1 on the unit circle. So right here, we're looking at just the top half of the unit circle as where we would evaluate inverse cosine. And those are going to be rotations from 0 to pi, right? So just like before, we can take a look at some rotations that cosine would evaluate and give us x values, and then we can look at those x values in terms of inverse cosine and talk about how we would evaluate those x values for rotation. So right here, if we start out with, let's say, 5/6 pi, 5/6 pi would be a rotation that took us into the second quadrant, that last stop. And with that rotation, we have the ordered pair that is negative square root of 3 over 2, 1/2. That means that the horizontal change we're going to see is negative square root of 3 over 2. Now, when inverse cosine evaluates negative square root of 3 over 2, it's going to say, what's the least amount of positive rotation that I need to generate that horizontal change? And it's actually going to tell us that it is the rotation 5/6 pi. So right here we would say 5/6 pi would be the least amount of positive rotation that would generate that horizontal change. Now right here, let's say I rotated all the way into the fourth quadrant. So let's say we rotated all the way around to, let's say, 7/4 pi. So this rotation, 7/4 pi, would generate a horizontal change that we could see on the x value or the perimeter of the unit circle. That would be square root of 2 over 2. And we'd see that in the ordered pair, square root of 2 over 2, negative square root of 2 over 2. So right here, for the rotation of 7/4 pi, cosine says that we have a horizontal change on the perimeter of the unit circle of square root of 2 over 2. Now inverse cosine is going to take that square root of 2 over 2, and it's going to say, what's the least amount of positive rotation I need to generate that horizontal change? And it's going to say the least amount of rotation I need to generate that horizontal change is a rotation in the first quadrant of pi over 4. Since when I rotate pi over 4, I get the ordered pair square root of 2 over 2, square root of 2 over 2, and I can see that horizontal change right there. And so right here, I would get the rotation of pi over 4 for inverse cosine of square root of 2 over 2. All right, guys, we're going to do one more. We got tan, and we would say that inverse tan, or arctan, is of course going to take y values divided by x values on the perimeter of the unit circle, and it's going to tell us what rotation we would need to get that ratio. So just like sine and cosine, we are failing the horizontal line test yet again. And right here, what we need to do now is figure out what the smallest interval of the domain would be that would generate all of the outputs of tangent. And right here, what we can say is that if we cut the graph of tangent from negative pi over 2 to positive pi over 2, we get basically all of the outputs for tangent. So right here, inverting this graph, we get a graph that looks something like this, where we have horizontal asymptotes at pi over 2 and negative pi over 2. And again, in general right here, this graph on its own isn't that much use to us, but we can identify the domain and range of the inverse more easily. Right here, we're going to say that the domain of inverse tan is going to be negative infinity to positive. The range for inverse tan is going to be from, but not including, negative pi over 2 to, but not including, pi over 2. And this means that we are going to be evaluating inverse tan on the right side of the unit circle, just like we evaluate sine on the right side of the unit circle. The one difference being that we will not be including negative pi over 2 or positive pi over 2 in the rotations that we evaluate inverse tan with. So let's go through and evaluate ratios of tan, and then look at how we're going to evaluate inverse tan. So right here, if I have a rotation of pi over 4, that is going to give me that middle stop in the first quadrant, where the ordered pair is square root of 2 over 2 for x and square root of 2 over 2 for y. So right here, tan would evaluate pi over 4 and give us the ratio of the y, square root of 2 over 2, to the x, would also be square root of 2 over 2. And that gives us the output of 1 as the ratio for tan. Now, inverse tan would evaluate 1, and we would have to see that 1 as a division where the y value is equal to the x value. And of course, that's only going to happen at those half-quadrant rotations, specifically the half-quadrant rotations that are either in the first quadrant or the third quadrant. But since inverse tan is only going to be giving us outputs from negative pi over 2 to positive pi over 2, that means that specifically this would have to be the square root of 2 over 2 divided by the square root of 2 over 2. And right here we see the y value of square root of 2 over 2 divided by the x value of square root of 2 over 2 at the rotation of pi over 4. So what we're seeing here is that we have to do a little bit more work for inverse tan in terms of interpreting that y value divided by that x value, because that's not going to be given to us as the y value on the perimeter of the unit circle being divided by the x value. It's going to be given to us in a simplified form. Let's look at another one of these. Let's say that tan evaluates the rotation that is 7/6 pi. So 7/6 pi is the rotation that goes 1/6 past pi into the third quadrant, where we have the ordered pair that is negative square root of 3 over 2, negative 1/2. So right here, we would have tan as negative 1/2 to negative square root of 3 over 2. But that reduces down to 1 over square root of 3. Inverse tan would evaluate 1 over the square root of 3. And we would see that as 1/2 over square root of 3 over 2. So a trick for evaluating inverse tan is wherever we see that square root of 3, we want to interpret it as the square root of 3 over 2. So if inverse tan is evaluating 1 over the square root of 3, we want to see that as 1/2 divided by the square root of 3 over 2, and that happens on the right side of the unit circle at a rotation of pi over 6. where we see the x value of square root of 3 over 2 and the y value of 1/2. So right here we would evaluate that 1 over square root of 3 as 1/2 divided by square root of 3 over 2, and that happens on the right side of the unit circle at a rotation of pi over 6. Okay, so we're going to give some of these a shot. We've got our unit circle here. We want to remind ourselves where we're evaluating these inverse trig functions. So inverse sine is going to take its input as a y value on the perimeter of the unit circle, and it's going to give its output as the rotation where we have that y value on the right side of the unit circle. Now what that means is that the rotations of 3/2 pi, 5/3 pi, 7/4 pi, and 11/6 pi are actually going to be given as outputs negative pi over 6, negative pi over 4, and negative pi over 3, with that final rotation as negative pi over 2. So we want to think about each of these stops as actually being a negative rotation down instead of a rotation all the way around into the fourth quadrant. Inverse cosine is going to give its rotations on the top half of the unit circle. So of course, inverse cosine will take as its input an x value and give the rotation where that x value happens on the top half of the unit circle. And finally, inverse tan is similarly to sine going to give its outputs as rotations on the right side of the unit circle, and it's going to evaluate the inputs as y values divided by x values. So let's take a look at some of these. We've got here inverse sine and inverse cosine expressions. What I want you guys to do is to go through and use the unit circle as we've altered it to evaluate these inverse trig functions. And I want you to also go down and look at inverse tan and see if you could evaluate those on the altered unit circle we have above as well. All right, guys, so taking a look at these, remember that the inputs are going to be ratios and the outputs are going to be rotations where we see those ratios on the perimeter of the unit circle. So right here, looking at inverse sine of 1/2, we're looking at where we have the ratio of y equals 1/2 on the perimeter of the unit circle, and we can say that that happens at the first stop in the first quadrant, so that would be pi over 6. If we're looking at inverse cosine of square root of 2 over 2, we're looking for where we have square root of 2 over 2 as an x value on the top half of the unit circle, and that's going to be that middle stop, or that half quadrant rotation in the first quadrant of pi over 4. If we're looking at where we have inverse cosine of negative square root of 3 over 2, that's going to be a rotation into the second quadrant that is 5/6 pi, 1/6 of pi in the second quadrant. Inverse sine of negative square root of 2 over 2 is going to be the rotation on the right half of the unit circle, where we get a y value of negative square root of 2 over 2, and that is going to be the rotation down, 1/2 quadrant rotation to negative pi over 4. Inverse sine of negative square root of 3 over 2 is going to be a rotation down again on the right side of the unit circle to negative pi over 3. That's the amount of rotation we would need to generate that vertical change there. When we're looking at inverse cosine of negative 1/2, that's going to be, again, a rotation that takes us into the second quadrant. And right here we can say that the amount of rotation we would need to generate that negative 1/2 as an x value would be 2/3 pi. If we're looking at inverse sine of 1, we're basically looking at where on the right side of the unit circle we would need to rotate in order to get a y value of 1, and that would be pi over 2. Inverse cosine of 0 is going to be the amount of rotation we would need to get an x value of 0, and that's rotation onto the y-axis, and so that would also be pi over 2. All right, so the inverse tans are a little bit tricky. We can get through these though. So in general right here, remember that everything we see inside inverse tan we want to interpret as a y value divided by an x value. So right here looking at this, if I have inverse tan of 1, I want to think what rotation on the right side of the unit circle do we have the y value and the x value equal to reduce down to 1? And that's, of course, that first quadrant rotation of pi over 4. All right, so right here, inverse tan of square root of 3, we want to see just the square root of 3 as the square root of 3 over 1, which means that we've got the square root of 3 over 2 divided by 1/2, right? So if we see square root of 3 in the numerator, we want to think about that as square root of 3 over 2 divided by 1/2. Now right here, the rotation that gives us that y divided by x as a ratio on the right side of the unit circle is pi over 3, right? And that's that first quadrant rotation, or that last step in the first quadrant. If we see 1 over the square root of 3, we want to interpret that as being 1/2 over square root of 3 over 2. So right here, if we have negative 1 over square root of 3, we want to think about that as being negative 1/2 over square root of 3 over 2. And again, that's because we're only evaluating inverse tan on the right side of the unit circle. So if inverse tan is negative, that means that the y value has to be negative. And that means it was a rotation down into that fourth quadrant. So right here, inverse tan of negative 1/2 divided by square root of 3 over 2 is going to be a negative rotation of pi over 6. So negative pi over 6 would be the amount we would need to rotate down in order to get that y divided by x ratio. Inverse tan of 0 is basically saying how much do I need to rotate to get 0 for my y and 1 for my x, and that would be 0 rotation right there, so that's how much we would rotate.